Infinite limits and the reciprocal function. Hello everyone. Let's begin today's lesson on infinite limits and the reciprocal function. Up until now, in our previous sections, we have focused on limits that result in a specific, finite real number. Essentially, cases where the function settles on a clear, predictable value. However, in mathematics, we often encounter situations where the function does not settle. In some cases, as the input variable x approaches a certain value, the output of the function simply increases or decreases without bound, meaning it keeps growing or shrinking forever. This specific type of behavior is what we describe using the concept of infinite limits. To help us truly understand how this works and how to denote it mathematically, we are going to analyze a primary example, the reciprocal function. Let's move forward and look at how this function is structured. The reciprocal function. Now that we have introduced the general concept of infinite limits, let us examine a concrete example to see this in action. Please look at the simplest reciprocal function, which is f of x equals 1 over x. If you analyze this expression, you will notice that we can substitute almost any value for x. In fact, this function is defined for all real numbers, with one critical exception. X cannot be equal to 0. This is because, as you know, division by 0 is undefined in mathematics. Consequently, we cannot evaluate the function at 0. In other words, f of 0 does not exist. Since we cannot find the value exactly at 0, we instead use limits to investigate the behavior of the function as x approaches 0. We will observe what happens as x gets closer and closer to 0 from both the positive and negative sides, which will lead us to understand why this function results in the infinite limits we mentioned previously. Approaching 0 from the right-hand limit. Now that we have established that the reciprocal function is undefined at 0, let's examine how the function behaves as we get closer to that point. We will start by looking at the right-hand limit. When we say x approaches 0 plus, we mean that x is approaching 0 from the positive side. In other words, we are looking at values of x that are slightly greater than 0. To understand this behavior, let's perform a step-by-step analysis by picking values for x that get progressively closer to 0. First, if we let x equal 0.1, then the function 1 over x equals 10. If we move even closer and let x equal 0.01, the value of the function increases to 100. And if we go even further, letting x equal 0.001, the result becomes 1000. As you can see, as x becomes smaller and smaller, while remaining positive, the value of 1 over x becomes larger and larger. Since there is no upper limit to how large the function can become, we say that the function increases without bound. We express this formally using mathematical notation. The limit of 1 over x, as x approaches 0 from the right, equals positive infinity. Having analyzed the positive side, we must now consider whether the function behaves the same way when we approach 0 from the negative side, which we will explore in the next slide. Approaching 0 from the left-hand limit. Now that we have analyzed the behavior of the function from the right, let us examine what happens when we approach 0 from the opposite direction. When we say x approaches 0 from the left, which is denoted by the small minus sign in the superscript, we mean that x is approaching 0 from the negative side, using values that are slightly less than 0. To understand this, let us perform a step-by-step analysis by picking values of x that get progressively closer to 0 from the negative side. First, if we let x equal negative 0.1, then the function 1 over x equals negative 10. If we move even closer to 0 and let x equal negative 0.01, the value of the function becomes negative 100. And if we take x to be negative 0.001, the result is negative 1000. Notice the trend here. As x becomes closer and closer to 0 from the negative side, the value of 1 over x becomes more and more negative. Since this value continues to decrease without any lower bound, we use the symbol negative infinity to describe this behavior. In formal mathematical notation, we express this as the limit of 1 over x, as x approaches 0 from the left, equals negative infinity. Real-world analogy, speed and time. Now, to help you visualize the abstract concepts we have just discussed regarding the reciprocal function, let us consider a real-world analogy involving the relationship between speed and time for a fixed distance. To start, recall the fundamental formula, where time equals distance divided by speed. Let us apply this to a specific scenario. Suppose you have to travel a fixed distance of 1 kilometer. If your speed is very slow, for instance, 0.1 kilometers per hour, it would take you 10 hours to complete the journey. If your speed drops even further to 0.01 kilometers per hour, the time required increases significantly to 100 hours. Notice the pattern here. As your speed approaches 0, meaning you are barely moving, the time required to reach your destination increases without bound, tending toward infinity. This scenario perfectly mirrors the mathematical behavior we analyzed in the previous slide, where the limit of 1 over x, as x approaches 0 from the right, equals positive infinity. In this specific analogy, the variable x represents your speed. Having seen how the function behaves as we approach 0 from the right, we must now ask ourselves a critical question. Does the overall limit actually exist at 0 when we consider both sides? We will address this in the next slide. Does the limit exist at x equals 0 backslash? Now that we have analyzed the behavior of the function from both sides, let's address the critical question. Does the limit actually exist at x equals 0? To start, let's review the general mathematical requirement for a limit to exist. For the limit of f of x as x approaches c to exist as a real number, the left-hand limit and the right-hand limit must be exactly equal to each other, and they must both result in a finite real number. Let's apply this criteria to our specific function, f of x equals 1 over x, as x approaches 0. As we discovered in the previous slides, the right-hand limit is positive infinity. On the other hand, the left-hand limit is negative infinity. Because positive infinity is not equal to negative infinity, the two limits do not coincide. Furthermore, it is important to emphasize that positive and negative infinity are not real numbers. They are simply symbols used to describe the behavior of a function that increases or decreases without bound. Consequently, since the left and right-hand limits are different and are not finite real numbers, we must conclude that the limit of 1 over x as x approaches 0 does not exist. Keep this distinction in mind, as we will summarize these key takeaways in the next slide and discuss some common mistakes students make when interpreting these results. Key takeaways. Now that we have analyzed the behavior of the reciprocal function from both sides, let us summarize the key takeaways from this lesson to ensure we have a solid foundation before moving forward. First, let's define the core concept, an infinite limit. As we discussed at the beginning, this is a limit that describes a function increasing or decreasing without bound as it approaches a specific point. In simpler terms, the output doesn't settle on a single number, but instead grows or shrinks indefinitely. Applying this to our specific example, the reciprocal function, f of x equals 1 over x, let's recall the right-hand behavior. We observed that as x approaches 0 from the right, the function f of x tends toward positive infinity. Similarly, looking at the left-hand behavior, we found that as x approaches 0 from the left, the function f of x tends toward negative infinity. Finally, this leads us to the conclusion regarding the non-existence of the limit. Because the left-hand limit and the right-hand limit are different, one heading toward positive infinity and the other toward negative infinity, and because these are not finite real numbers, we must conclude that the limit of f of x as x approaches 0 simply does not exist. With these fundamental points clear, let us proceed to the final slide, where we will discuss some common mistakes students often make when dealing with these concepts. Common mistakes. Now that we have covered the core concepts and the key takeaways, let us address some common misconceptions to ensure you avoid these pitfalls in your assignments and exams. First, a very frequent error is treating infinity as if it were a specific real number. For instance, some students might mistakenly attempt to perform arithmetic with it, such as calculating infinity minus infinity and concluding that the result is 0. It is crucial to remember that infinity is not a coordinate or a value on the number line. Rather, it is a mathematical notation used to describe unbounded growth. Secondly, there is often a misunderstanding regarding whether a limit actually exists when a function increases or decreases without bound. You may see us write that the limit of a function equals infinity to describe its behavior. However, in strict mathematical terms, specifically within real analysis, we say the limit does not exist because, by definition, a limit must be a finite real number to exist. Using the infinity symbol is simply our way of being more descriptive about why the limit fails to exist. Finally, please be careful not to ignore the sign of the approach. As we demonstrated in our step-by-step analysis of the reciprocal function, approaching 0 from the right, which we denote as 0 plus, results in positive infinity. Conversely, approaching 0 from the left, or 0 minus, results in negative infinity. I strongly encourage you to always check the sign of your input when dealing with reciprocal functions to ensure you are identifying the correct direction of the limit.